So I want to talk now about a second strategic partnership. Today's sophisticated products are getting smarter. There's more and more electronics on board. And engineers want to see how these products interact electrically with the environment. So it's very, very important that we can cover electromagnetics. So the way we're doing this is we're partnering with a leading provider in electromagnetics. And that provider is CST, stands for Computer Simulation Technology. We're actually going to issue a press release about the strategic partnership tomorrow morning. And to tell you about CST and how CST is going to power innovation in the electromagnetics realm, I'd like to bring on stage Dr. Bernhard Wagner. Dr. Wagner, thanks so much for coming to our SEC. I'm very excited you're here. You wanted to start with a short video.
Yes, that would be great.
Designing electronic components and systems is a challenging task, one made even more challenging because you can't usually predict how your designs will hold up in a real-world setting. And that's where computer simulation technology comes in. We build software to simulate electronic components and systems, from those found in smartphones to those found in aircraft carriers, allowing you to see how they will work and even optimize their performance well before you manufacture them. There are many factors that go into an effective system or device. From component interoperability within your electronic system to understanding how certain electromagnetic devices will react to environmental hazards and limitations. At CST, we cultivated over 20 years of electromagnetic simulation experience to bring you CST Studio Suite.
Wow, okay. Very excited. So I'm going to leave it up to you and tell us how you're going to power innovation.
Thank you, Bruce, for the nice introduction. Ladies and gentlemen, I'm very pleased and excited to be here today to give you a short summary of what CST does and what we can do best. My name is Bernhard Wagner. I'm one of the 3 directors who have been running the company for the last 2 decades almost. There is a nice coincidence. We had our user conference here in Berlin as well last year. But as you can see, our audience is not as large as the audience in this room. And this is simply because the market for EM simulation is not as large as the market for structural or safety applications. However, EM simulation is gaining importance, and we will see what the drivers are for this. CST was founded in '92 as a spin-off of University of Darmstadt, and it started with just a couple of PhDs who were passionate about Maxwell's equations. And today we are 270 employees distributed over 16 countries in the world. I don't want to spend too much time on the past, just mention maybe 3 major milestones that have helped CST to grow faster than the overall market. So in '98, we released Microwave Studio. CST Microwave Studio was the most intuitive program at the time. People are still excited about this famous version number 1, which was kind of revolutionary because it was so easy. We tried very hard to prove that our method, and we were the time domain guys, that our method was superior for all applications. But after several years, we had to learn, we understood that no single method will win the fight. And so we introduced what we call complete technology for EM, which means that we introduced or implemented all major numerical methods in one single interface. And this means that the user can now select the best method for each application. And I think we are quite unique in this regard and pioneers in what we call complete technology. But today, it's not just about single components. It's more and more about systems. So we introduced a new technology concept that helps to simulate very complex systems. But what can all this be used for? You may have seen a short introduction in the video, but I'd like to give you some more examples. But if I tried to give you a complete overview of all applications, I guess we would probably miss dinner tonight, and I guess no one of us wants this. So I've selected just a few examples that affect us in our daily life. So let's see what happens to this charming family during a normal working day. So here we see Sarah and Paul at breakfast with their kids, and Paul likes to heat his porridge in the microwave oven. And a well-designed microwave oven is not as easy to manufacture. It should have a safe shielding, it should be energy efficient, and it should heat the food most evenly. I guess you have all made that experience that food can be cold and hot in different corners. And if that happens, it's maybe not a well-designed microwave oven. And I can assure it was not designed with our software in this case. So after breakfast, maybe Sarah is commuting by bus, and in this modern bus, there is a transmitter, a Wi-Fi link. And simulation has found the optimum location for this transmitter so that there is good coverage at all seats. But most importantly, it was simulated that there is no interference with other communication systems in the bus. And this is even more important in the case of a modern car. A modern car can have easily up to 40, 50 antennas for communication, navigation, entertainment, or safety. In this case, we see a scenario of a vehicle-to-vehicle communication. So the left car emits some waves that are partially reflected in the car in front. And the challenge here is to combine very fine details, such as this rooftop antenna from Audi, or a cable harness, that you can see at the right-hand side, with a complex structure such as a chassis of a car. And this is what I meant earlier, that we need a smart technology to assemble and simulate all these parts together. So let's assume that Paul is driving in this car, and he's on his way to a new location for a wind turbine that his company has manufactured. And so maybe in the early design stage, he had to simulate how the immunity works when it comes to lightning strike, and now he's maybe concerned about how the blades influence the radar system of an airport, which may potentially be close by. So, and then half through the afternoon, he gets a phone call. And although he's in a quite remote location, the reception is surprisingly good because there is a multi-antenna system inside the 4G phone. And our software helps a lot of mobile phone manufacturers to design their antennas and optimize their antennas. But simulation is also used to show how the fields penetrate into the head during a call, and it's maybe not that much known that about 70% of the energy is absorbed in the human body. So, and Paul receives maybe some bad news. So his daughter has fallen at school and hurt her shoulder. But the good news is here that the local hospital has a very good MRI system that gives perfect pictures with a high resolution, and there is apparently no serious damage. I just want to mention that this, to give you one more example, because EM fields, electromagnetic fields, are used in the case of many medical devices. And there is a very interesting research going on at Stanford University to replace the traditional pacemakers by very tiny little pacemakers that no longer have a battery. So you don't need to go to the hospital, have a surgery every 10 years to replace the battery because the energy is fed from the outside. So let's see if that is something that we'll have in the future. So in the evening, everyone is safe home, maybe relaxing in front of the TV or checking emails on a tablet. And we all know, I mean, wireless and electronic devices are all around ourselves, and the Internet of Things accelerate this process even further. So I hope that this small selection of examples has shown that EM simulation plays an increasing role in the design of many, many products, and this in fact has led to discussions with Dassault. So we entered discussions, and as we've seen from Bruce, we've decided to form a partnership, and I'm very happy, that we're really starting, and in fact we have already started. The teams from SIMULIA and CST have met several times, and we will do a couple of things. We will provide a good interoperability between the products, and we will also develop specific eMAC applications for the 3D Experience platform. And R&D teams have already started to implement a couple of workflows that, for which we have identified an important need. For the first example is a satellite antenna, and we assume that the satellite antenna is heated in the sun and therefore deformed, and even if the deformation is small, it still changes the far field pattern of the antenna in a not neglectable way. And this is an example for sequential simulation flow. But then we have another example where an object is heated by induced currents, and those induced currents make that object so hot that the material properties change. And this example requires multiple iterations between Abacus and the CST software. So it requires a better technology that the R&D teams are working on now. I don't want to, or I don't have the time to go into more details, but I'd like to draw your attention to a presentation tomorrow at 2:15 p.m. And there you can learn more about these examples and what we plan to do in terms of co-simulation and in terms of links. And before coming to the end, let me say that I'm very happy that the cooperation has started so well. We felt from the beginning that there is a good cultural match between the teams. Both teams are very technology focused and solution oriented. We also like the vision of Dassault, I have to say, to improve product, nature, and life. And we are excited to help to contribute to this vision with our expertise in technology. Thank you very much for your attention.
Thank you, Bernhard. Thank you, Bernhard.
Okay,
That was great.